Hi, this is Dr. Alt. I'm going to show you a demonstration of sample question number 2 that was issued in class today. Patient is abducting their arm to 90 degrees. So I draw a picture of my patient abducting their arm. It tells me, and I'm going to just draw in the deltoid muscle. It tells me that the distance from joint axis to deltoid insertion is 4 inches. That will be little d. It's not the IMA, it's the distance from joint axis to tendon insertion. So little d is 4 inches. The angle of deltoid insertion is 20 degrees. So the angle of deltoid insertion is 20 degrees. The weight of the limb is 15 pounds acting 10 inches from the joint axis. So the distance, which would be my external moment arm that I could just call external moment arm number 1, that's related to the weight of the limb, is equal to 10 inches. And it's 15 pounds acting in a downward direction. I am holding 10 pounds in my hand, acting in a downward direction, and that distance from joint axis to tendon insertion, I could call that external moment arm number 2, is 24 inches because it's all the way out in my hand. I draw my free body diagram, I label what is known, and the first thing I begin with is setting up my moment equation. I'm going to start with the 2 external weights. 15 pounds acting in a downward direction at a distance from my shoulder joint is going to create a rotation in this direction. So pushing down will create this sort of rotation, and that is clockwise. The 10-pound weight acting down will also create clockwise torque or rotation. So when I set up my equation, clockwise equals counterclockwise, I'm going to have 2 things on the clockwise side. That will be balanced by my muscle force of the deltoid, but since the D that I'm given is joint axis to tendon insertion, it's only going to be this rotatory component times the little d, creating rotation in a counterclockwise direction. So for counterclockwise, I will have muscle force rotatory times the little d. That will be balancing 15 pounds, the weight of the limb, which is acting 10 inches from my joint axis, intersecting at a perpendicular, plus 10 pounds weight in my hand times 24 inches, the distance it is acting away. And my little d, I know, is 4 inches. So if I do my math correctly, that is 150 pound-inches. Note, torque will always be a force distance measure. It might be pound-inches, it might be Newton-meters, it might be Newton-centimeters. Just take time to record your units, because if you don't, it is likely to get you into trouble. Then I have 240 pound-inches. That is equal to my muscle force rotatory times 4 inches. I add that together and I have 390 pound-inches, and I'm going to divide that by 4 inches, and I will end up with a muscle force rotatory equal to 97.5 pounds. If the question is, what's the muscle force required to hold the system in equilibrium, I have not yet answered the question. I have only calculated the rotatory component. So now to calculate the resultant muscle force, I will use my sine of theta is equal to opposite over hypotenuse. I am solving for the resultant muscle force. I know that the angle of tendon insertion, I just redraw it here for you, the angle of tendon insertion is 20 degrees. I know this muscle force, rotatory, I am trying to solve for the resultant. If this is 20, this is 20. Sine of theta will be equal to the opposite over the hypotenuse. That means my muscle force rotatory over my resultant muscle force. If I solve for the muscle force, I will have muscle force rotatory divided by the sine of 20 degrees. I've just calculated my rotatory muscle force equal to 97.5 pounds divided by the sine of 20 degrees, and I get my muscle force equal to 285 pounds. Have I answered my question? What's the muscle force required to hold the system in equilibrium? The answer is yes, and I have completed that question. I already know that it's acting at 20 degrees, and this is its magnitude. That's the end of part 1.